every single stretchy thing out there, whether it's a tiny rubber band or a giant bridge cable, kind of has its own personality. Some are really stubborn and stiff, right? And others are super loose and easygoing. So today, we're going to dive into how physics actually describes that personality. And more importantly, what happens when you push it way past its limits. All right, so let's start with a little puzzle. What on earth could a huge, bouncy trampoline possibly have in common with that tiny little spring inside your ballpoint pen? I mean, they seem like they're from different planets, but believe it or not, they operate on the exact same incredibly simple principle of physics. And here it is. This is the core idea. It's something we all just get. You pull on something, it stretches. And the harder you pull, well, the more it stretches. This super simple, totally predictable relationship is the foundation for absolutely everything else we're going to talk about. But just saying something is stretchy isn't exactly scientific, is it? We need a better, more precise way to describe this whole thing. How do we actually put our finger on the difference between something that barely budges and something that seems like it could stretch forever? Well, let's break it down like this. On one side, you have something really stiff. Think about the suspension on a car. It takes a massive amount of force just to get a tiny bit of movement. But then on the other side, you have something loose, like a slinky, right? The slightest little push sends it stretching way, way out. That's the fundamental difference we're trying to pin down. So how do you capture that entire stiff versus loose personality in a single number? Well, physicists came up with a pretty brilliant and simple way to do just that. And that number is called the spring constant, which we just call K. You should think of K as the object's unique stiffness fingerprint. A really high K means it's super stiff, like that car suspension. A low K means it's really loose, like our slinky. It tells you exactly how much force it takes to get 1 inch or 1 centimeter of stretch. And this is how we find it. This formula is a huge deal in physics. It's called Hooke's Law, and it's beautifully simple. K is just F divided by X, where F is the force you're applying and X is the extension, how far it stretched. Force per extension. That's it. Okay, so this isn't just some abstract idea in a textbook. Let's look at how you'd actually use it. It's a practical tool, and you can find the K value for pretty much any spring with just a couple of simple measurements. So here's how you do it. First, you apply a force that you already know. Let's say you hang a 10 Newton weight on your spring. Easy. Second, you measure the extension. You look and see it stretched, say, 2 centimeters from where it started. And third, you just divide. 10 newtons divided by 2 centimeters, that gives you a spring constant of 5 newtons per centimeter. And boom, just like that, you've captured its personality in a single number. So for a while, everything is going great. It's all perfect and predictable. More force in, more stretch out. But this perfect little relationship has a dark side. There's a point where the rules don't just bend, they break. And that's really the crucial thing to remember. This neat, tidy, predictable world doesn't go on forever. If you push too hard, you go beyond just stretching something elastically, and you enter the zone of permanent damage. Every single material, no matter how tough you think it is, has a breaking point. So what does that actually look like? Imagine you've got your spring. You've calculated its K value, everything is behaving exactly as it should. But you just decide to keep going. You keep adding more and more and more weight. What eventually gives? This brings us to the most dramatic part of our little spring's life story. We're talking about the point of no return. It's a specific, measurable moment where everything we thought we knew about that spring changes, for good. The easiest way to picture this is on a graph. So in the beginning, the good part, you get this perfect, straight, diagonal line. You double the force, you double the stretch. Makes sense? But then you hit the turning point. All of a sudden, the line starts to curve. And what that means is you're getting a lot more stretch for just a little bit of extra force. And once you go past that bend, it's over. The relationship is broken, and that spring is never, ever snapping back to its original shape. Now, this turning point has a fancy scientific name, of course. It's called the limit of proportionality. It is the exact moment where that perfect straight-line relationship we saw, Hooke's Law, stops working. And let's be absolutely crystal clear here. Once you stretch a material past this limit, it is permanently damaged. You have literally pulled the molecules inside it into new positions, and they can't get back. A spring just becomes a sad, saggy piece of metal. A climbing rope loses that bounce that makes it safe. The damage is done. So, okay, why should you care about any of this? Because understanding both the spring constant and this limit is absolutely vital for safety and engineering. Designers need to know how stiff a material is, that's its K value, so it does its job right. But they also have to know its absolute limit, so that a bridge doesn't permanently bend, a trampoline doesn't get saggy after one summer, and a climbing rope can actually absorb the energy of a fall and save someone's life. And that kind of leaves us with one last thing to think about. If you were the engineer designing one of these things, which of these two ideas would keep you up at night? Would it be the day-to-day performance, its stiffness, or would it be that absolute catastrophic point of no return, its limit? Definitely something to chew on.